Welcome everyone. In this video lecture, we will discuss a very important concept, that is our channel length modulation. In addition to that, we will also discuss the finite output resistance in the saturation region. Okay. In addition to that, we will also discuss finite output resistance resistance calculation. Okay, which is basically in the saturation region. Okay. So and also we will derive the expression for the channel length modulation. That should be the drain current equation. So this one is the basically one diagram I have already made. So this in the source and drain. So basically what happens when this VDS, the voltage across the drain and source, I am writing here, this VDS is greater. Okay, if we will increase this VDS just slightly greater than VDS set. Okay, so there will be a shift of the channel. So there will be basically there will be a shift in the channel length towards the source in. Okay, if VDS is greater than VDS set, okay, means when I am saying this voltage, this voltage, okay, is just greater than or more greater than VDS set. So there will be shift in the channel length towards the source in. So this will cause, so suppose initially it is a channel length L. So there will be shift of somehow some distance del. So the channel length, the equivalent channel length will be, so I am writing here equivalent channel length, channel length after the drifting will be simply L minus delta L. This is the very important, means in channel length modulation what happens, basically the actual channel length is somehow shifted towards the source by L minus delta L. Basically this one is del L. So the overall shift in this one will be the actual or equivalent, or sometimes we can say this one is actual channel length. Okay, or we can write as a, better to write actual channel length will be L minus delta L. So this one is the concept. So basically what happens, the voltage across the channel remains constant. Okay, it means the VD set equals to VGS minus VT. Okay, the voltage across the channel remains constant. Okay, and the additional voltage applied, okay, and the additional voltage applied across the drain region will be appeared as a voltage drop across the narrow depletion region, okay, between the end of the channel region and the drain region. Okay, so I am taking this all concept from the microelectronics book. I am also writing, you can also microelectronic circuits book by Sir Smith. Okay, the same thing I have taken, but this is the concept. So basically in this region the VDS set will be constant, but when we increase somehow the VDS voltage, so the extra voltage appears across the drain to source region will be dropped across the narrow depletion region, and the end of the channel region. So the voltage accelerates the electrons that is the drain in of the channel and sweeps them across the depletion region. So this is the very fundamental, means we have to think about, means in channel length modulation it is somehow shifted towards the right. Okay, so now we have to discuss the, means what should be the actual expression. Okay, so now as we know the drain current, and it is done, this kind of things will be done for the saturation region case. Okay, this one will be appear in the saturation region. So this one is one more diagram, more actual diagram for lambda greater than 0. We will discuss what is lambda. So we will discuss it later. So this can be appear in the saturation region. So first of all, we have to write the drain current equation in the saturation region. So I am just writing 1 by 2 mu n Cox W by L Vgs minus Vt whole square. The fundamental drain current equation in the saturation region, because this thing is happening for the saturation region. Vds should be greater than this. Vds should be greater than equals to Vgs minus Vt. Okay, so this will come under the saturation region condition. Okay, so now next what we can write, the ID expression means how we have to derive the uh, means the expression. So the channel length, actual channel length will be not L, it should be L minus delta L for the L minus delta L. Okay, Vgs minus Vt whole square. Okay, so the ID expression, actually we are going to derive the main equation in terms of lambda, channel length modulation parameter lambda. Okay, so now once again one can write 1 by 2 mu n Cox W, and if we take L common, one can write 1 minus delta L by L into Vgs minus Vt whole square. Okay, very simple. I am not writing directly the equation first, we will derive. Okay, means how to derive the expression. So ID can be written as 1 by 2 mu n Cox W by L, and this can be written as 1 minus delta L by L. Okay, simply. Okay, inverse into, here we can make it into Vgs minus Vt whole square. It is a threshold voltage, get to source voltage. One can also write override voltage Vgs minus VOV, but I am writing like this. So now this ID. Okay, now one thing here, this delta L by L will be very less than 1. So one can directly write the expression for this one, 1 by 2 mu n Cox W by L 1 plus delta L by L. Okay, means 1 minus a to the power minus 1 will be 1 minus of 1 means 1 plus a simply. Okay, minus. Okay, so directly we can write this one is just the expansion, x minus y to the power n. So minus 1, so 1 minus of this minus 1 into del. So simply one can write 1 plus delta L by L. Okay, into, okay, into Vgs minus Vt whole square. Okay, so this one is the expression. Now what we can do now, ID once again I am writing 1 by 2 mu n Cox W by L. Okay, now what we can do, delta L, that is our the channel length, this one is shifts by say delta L. So delta L is somehow dependent on the voltage across the drain to source. This del L will be somehow dependent on the VDS. So this delta L, if we put some proportionality constant, say lambda dash, so it should be VDS. Lambda delta L equals to lambda dash VDS. So one can write this as a 1 plus lambda dash VDS by L into Vgs minus Vt whole square. Means this delta L is somehow dependent upon the drain to source resistance. So I am just putting this is proportional. So lambda dash one some proportionality constant we can say, and this delta lambda dash can be called as the process technology parameter. Technology parameter. Okay, having unit meter by lambda dash, meter by volt. Okay, so basically this one is in general micrometer by per volt. Okay, micrometer. Okay, meter by per volt. This lambda dash. Okay, this is important. Once again, I am highlighting this point. Okay, delta L, del L is proportional to supply voltage. So now this one we have written like this. Okay, so once again we can sort this expression. ID equals to 1 by 2 mu n cox w by L 1 plus. Now I am just going to write this term lambda dash by L as a lambda. One more constant. What I am writing means I am writing lambda dash by L is some constant, say lambda. This one is also we can say process technology parameter. This one all are process technology parameter, but this process technology parameter with a unit. This one is also process technology parameter. Okay, with unit lambda. So lambda dash is micrometer volt, so it should be simply our volt inverse. Okay, because this lambda dash is having to be micrometer by volt, so micrometer and this one is also micrometer, micrometer cancel, so it should be voltage inverse. So I'm just writing lambda dash by L as a lambda. Okay, so this one is also very important observation. Okay, I'm just taking different color. Okay, this one lambda. Okay, so the overall expression we can say this one, the id equals to 1 by 2 bu1 cox w by L 1 plus lambda vds minus vt whole square. So this one is a very fundamental equation for the drain current in the saturation region by using the concept of channel length modulation. The exact expression with channel length modulation will be id equals to 1 by 2 mu n cox w by L. This should be vgs minus vt whole square. Very simple, the first term, but one additional term will be there, 1 plus lambda vds. So this one is the main expression and very famous equation, okay, for the then current in the saturation when we are considering the channel length modulation, and this lambda is a process technology parameter with unit this one. Okay, so basically what this one is a very early effect kind of thing. Okay, very similar to the BJT. If there is a plot between id vds for different get to source voltage minus vt, the overdrive voltage, this all are VOV, overdrive voltage. Okay, okay, so this one is basically our VOV. VGS minus VT is our overdrive voltage. Okay, overdrive voltage. Okay, so then after we can id equals to this one can write. So if we plot the basically for lambda equals to 0, this line will be flat. But if we extrapolate the this line drain current equation, id vds curve in the this direction, if we extrapolate, then it will come to near that some point like this. So this voltage is a va minus va, which is just simply minus 1 by lambda. So here the vds, what we can write, I'm writing here this vds equals to minus va, or this va equals to what we can say 1 by lambda. Okay, because this was the drain to source voltage, and if we extrapolate this point, so there will be one point that is our va, that is our minus 1 by lambda. Or in general this one is also called the all, sometimes we are saying this is a process technology parameter, and this va can be written as va dash into L. Okay, entirely process technology dependent with the dimension. Okay, and this VA dash, as per the microelectronics circuits book, the range is somehow 5 volt per micrometer to around 50 volt per micrometer. This one is also very okay. So okay, wait. So this VDS is somehow come near to one particular point, that is our 1 by lambda. So 1 by lambda is because this lambda is our having unit, lambda having unit volt inverse. Wait, I am writing here. This lambda having unit voltage inverse. Okay, so 1 by lambda, 1 by lambda is nothing but simply unit volt. Okay, so this volt, that is our, and this one is somehow some voltage unit. Okay, so this VDS, if we go in this direction, this one can be written as VA equals to 1 by lambda. So but this VA is negative, so one can also write directly, if we neglect the negative x-axis, so we can write directly VA equals to 1 by lambda, or minus VA equals to minus 1 by lambda. So that's why we are just representing this as the early voltage, say VA 1 by lambda. Okay, so this one is also very important point. And during for this point, the drain current, the ID value, ID or ID value will be 0. Okay, sometimes writing with the capital letter, or you can also write in that book ID as a small ID. Okay, so now we are following like this, so we can write. So when id is 0, id is 0, okay, 1 plus lambda vds. When id is 0, because this one we can simply find using this expression. When id 0, id 0, so 1 plus lambda vds equals to 0. So vds equals to minus 1 by lambda, so which is basically our minus va. Okay, so this one is the early voltage. Okay, that's why we are writing like this. Clear this one? So vds equals to minus 1 by lambda, or va equals to 1 by lambda. Clear? So now what we have to do, now we are going to discuss the output resistance. Okay, we can say the finite output resistance calculation. Finite output resistance, finite output resistance calculation. Okay, so in general what we can say, the finite output resistance R naught can be written as the output resistance. We can also write as output resistance. I am not writing. Basically this can be written as id by vds inverse, because we know this one v equals to ir. So r equals to v by I, or sometimes we can write it I by v inverse. Why I am writing? Because this one is expression as a id and VDS. So if we differentiate this equation, I am writing first that expression for ID equals to 1 by 2 mu n cox w by L VGS minus VT whole square 1 plus lambda VDS. If we differentiate, or here you can also write del ID by, if we differentiate del ID by del VDS. Okay, so what we will get, 1 by 2 mu n cox w by L. This should be as it is VGS minus VT whole square. 1 is constant, so 0, 0 plus lambda VDS. VDS will be 1, so lambda. So one can write lambda by 2 mu n cox w by L VGS minus VT. Simply we are just differentiating d by dVDS of 1 plus lambda VDS is simply our lambda. Okay, so now this will be what one can write, del id by del vds, or simply if we write this as a, okay, d VDS by dID equals to, one can write 2 by lambda mu n cox w by L VGS minus VT whole square, or we can write it 2 by lambda into ID, drain current equation, 2 by lambda ID. Okay, very simple, ID. So in general, what we can do, the R naught value will be what? This one is del VDS by del ID. Okay, or we can write this as a del VDS by del ID, same thing. Okay, these all are the same expression. Okay, so I'm just giving the brief that how to find. So this R naught will be 2. Okay, sorry, this 2 will be removed because the expression of that ID in the simple situation without when lambda equals to 0. This one for lambda equals to 0. When we are not considering the channel, it should be 1 by 2 mu n cox w by L VGS minus VT whole square. So ID at lambda equals to 0 and not yet. So 1 by lambda ID. So R naught and 1 by lambda can be written as, this one will be our 1 by lambda ID. So this one by lambda can be written as VA by ID, because this one is VA, where I have written this one. 1 by lambda is our VA. Okay. So this VA is just 1 by lambda from the process technology parameter. This 1 by lambda, VA is 1 by lambda. Okay, monthly voltage. So this one is simply our VA by ID. Okay, or in general we can write del VDS. So if we write the full means expression, so we can also write 2 by lambda mu n cox w by L VGS minus VT whole square. Okay, so this is the final expression for the output resistance. Okay, output resistance, clear. So this one is very easy to calculate. Okay, but we have to very careful about all this expression, means how to start, and these all things are happening using the device is in the saturation region. Okay, one can also write 1 by this by inverse. Okay, means one can also write the same expression in book, but this one is okay. 1 by lambda id va by id 2 mu. Okay, so if you have to draw the final means large signal equivalent model, so if we draw the, okay, so this should be our gate side, it should be drain, and this should be source and large signal model. So this should be some, and this finite output resistance will be our R naught, this R naught, and this will be the current equation half mu n cox w by L VGS minus VT whole square, and this one is our plus minus get to source voltage, and this one is the plus or minus VDS. So basically this one is a large signal model with output resistance, and so I am writing large signal model with output resistance, with output resistance. Okay, so this one is also important. So in the next video I will try to make a numerical from the microelectronics circuits book by Smith. So the main expression is this R naught and the drain current equation ID with lambda channel length modulation 1 by 2 mu n cox w by L everything will be same, VGS minus VT whole square with an additional term 1 plus lambda VDS. So this one is also important, and VA equals to 1 by lambda. Okay, this one is the, and this one is sometimes also called the early effect. So basically this formula is also important. So, and one expression also we have, write VA equals to VA dash into L. Okay, from the very above. Okay, from here VA dash equals to just VA by L. Okay, so this one is also important, VA dash, because initially we have this one is lambda, so 1 by VA. Okay, lambda is your 1 by VA, so lambda dash by L is nothing but simply our 1 by VA. So VA dash, so one expression we are writing VA equals to VA dash by L, to making the unit as a volt. Okay, so that's why VA dash into lambda. Clear? This one. So this is all about this simple uh, problem, means verification of different parameter for channel net modulation. So thank you for watching this video.